in many cases, be very straightforward to calculate. So let's work our way up there, and let's first just focus on flux through a closed surface. So what we're imagining is that we have three objects that are three-dimensional objects. Maybe they're like, we're just looking at it on this edge, and they extend out some distance, through your screen. And what we're doing is we've visualized, or we have some knowledge about the flux present at the surfaces. And you can see the different flux, the different electric fields indicated by the vectors in the problem. Okay, the question here is, which of these closed surfaces have zero electric flux? So let's have you guys answer that. Which of these have zero electric flux? Okay, good. Let's go ahead and end and share the results. So the most popular answer was A, that surface A has zero electric flux. So let's see if that's the case. So we can draw the area vector, right? This area vector for a closed shape, remember we said yesterday, points out from the center of the surface. And now I can say, let's call this surface 1, this surface 2, and say this surface 3. I know that total flux through this object is going to be the sum of the fluxes through each face. Flux 1, flux 2, and flux 3. Well, we can see, I should have called, 1, 2, and 3. We can see that flux 3 has to be equal to 0, that we don't see any electric field, right, entering the third face there. So that flux is 0. And here we can see that, right, the A vector is, right, I have this, right, if I shift over, here's the electric field here, and here's the electric field here, that I'm going to have some negative flux through surface 1 and some positive flux through surface 2, and that this angle, right, if I call this angle theta, that this guy is 90 degrees plus theta. And so all that's going to change between those two when I do the dot products of E and my area vector is the sign, and I'm going to get a negative contribution. Remember, the electric field flowing into the object gives a negative flux. The electric field flowing outwards gives a positive flux. And since I have identical surface areas and equal magnitudes of those electric fields, I get that the total flux is equal to 0. So I see this guy has to be equal to minus flux 1, and so this whole thing has to cancel out and give me 0 electric flux. What about B and C? Well, this guy, right, the A vectors point radially outwards, so all three of these electric fields would give me positive flux, so I would have a total positive flux in this case. And for this guy, I can see that the electric field is entering in all three surfaces, so I get a negative flux contribution from each of the surface, and I'll have a total negative flux. Okay. So what about this guy? I have a box, and the electric field is shown, shown, right? And I have different electric field present at, right, at the 6 different surfaces. Can we say something about the charge that's contained inside of this box? How much charge is contained in the box? Remember that Gauss's law tells us that the total flux through that surface has got to tell me about the charge enclosed inside of the surface over epsilon naught. So what do we think? Is there positive or negative charge inside of this box? All right, I'm going to give you guys about 15 more seconds. Okay, I'm going to end the poll. So we had a split decision here that, right, pretty evenly split between A, B, C, and some on D. So let's see how we're going to do this. We know that the flux through each surface is going to be E dot A. Let's draw those A vectors. So remember, those A vectors point outwards from a closed surface. That's our convention here. And each of these surfaces has the same size. So each of these A vectors points in a different direction but has the same magnitude. Right? And so we can see that, for instance, up here at the top, I've got this 15 nanocoulomb or newtons per coulomb electric field entering the surface, and I have that, and it's anti-aligned with A. Right? Remember, this is EA cosine theta. So the angle between those two is 180 degrees. It means that the flux is going to be negative, right? That cosine term is just going to give me -1. So I know the flux, right? If I change these field values into fluxes, this has got to be -15 times that, whatever the area of that box is. For this guy, I see that it's aligned with my area vector, so this is going to be a positive 20A for the flux. This guy, it's aligned, so it's going to be a 15A. This guy, it's anti-aligned, so I'm going to have a contribution to the flux that's like -20A. This guy is also anti-aligned, so it's going to be -15A. And this guy is aligned, so it's going to be a positive 10A. And then if I want the total flux, what am I going to do? I'm just going to sum all of those individual fluxes through each of the faces here. So here I can see I have a positive 15 and a negative 15. Those just cancel each other out. Here I see I have a positive 20 and a negative 20. Those fluxes will cancel each other out. And here I can see I have a positive 10 and a negative 15. So I end up with a net flux here of something like -5 newtons per coulomb times whatever the area of that object is, of one of those faces. And since that total flux is negative, that tells us that the charge has to be negative, right? If this guy is less than 0, it means this guy has to be less than 0 as well, because there's an equality sign between those two. So I can see in this case that I should have a negative charge inside of my box. Okay. All right. What about this problem? I have two Gaussian surfaces that I've drawn, A and B. And inside of each of those Gaussian surfaces, so the Gaussian surfaces are indicated by these kind of peach-colored spheres here. And there's some charge inside of each of them. And on A, there's a positive charge of Q, and in B, there's a positive charge of twice Q. Which one of those two surfaces has the larger electric flux? Which one has the larger flux? Okay, most of you selected B, and that's correct. Why is it B? Because Gauss's law tells us that the flux, the electric flux through the surface, is just equal to the enclosed charge. It doesn't care about the shape of the Gaussian surface. It doesn't care about where the charges are located inside of that Gaussian surface. The flux just depends on the total amount of charge contained inside of the Gaussian surface. And since here I have more charge contained inside of my Gaussian surface, I have more flux through that Gaussian surface. How much more? I should have twice the flux because I have twice the charge. What about this one? Now I've picked two Gaussian surfaces that are identical. They're both spherical Gaussian surfaces of radius big R. And I have the same amount of charge inside of both of them. It's just in B that charge is spread out over a larger volume, but it's still completely enclosed inside of my Gaussian surface. Which Gaussian surface has the largest electric field? Which one has we're not talking about flux now, we're talking about the magnitude of the electric field. Is the magnitude of the electric field stronger at the Gaussian surface for A or for B? Or are they the same? Okay, let me go ahead and end the poll, share the results. Most popular answer was that they're the same electric field and some other mix of A and B. Well, let's remember Gauss's law tells us that the total flux, which I could integrate the electric field over these little surface areas, right, over these tiny little surface area windows that spread across the surface, has got to tell me about the total enclosed charge over epsilon naught. Well, Q enclosed is the same for both of these, right? Even though that Q is spread out differently, the same amount of charge is inside of each of those Gaussian surfaces. So the right-hand side of this integral is the same. The dA bit, right, this integral, the area bit of this thing, right, is going to be identical too because I have the same Gaussian surfaces that I choose. And so in order to get the same Q, right, the right-hand side and the left-hand side to balance out, the only other piece is E, and so I have to have identical electric fields, right? If the Q enclosed is the same, the flux through each of them has to be the same. If they're identical Gaussian surfaces, that implies that the electric field has to be identical at those surfaces. So these have to have the same electric field sitting at the surface. What about this one? I have an electric dipole, a positive and a negative charge separated by some distance, enclosed inside of a Gaussian surface that I've drawn for you. Which of the following statements is true? That the electric field is zero everywhere on the Gaussian surface, that the electric field is not zero everywhere on the Gaussian surface, or whether or not the field is zero on the surface depends on where the positioning of this dipole inside of the Gaussian surface. So what do you think about the electric field? Again, I'm asking about the electric field value at the surface. Okay, I'll give you about 5 more seconds. And let's end the poll. So a lot of you selected that the electric field is everywhere zero on the surface. Okay. Well, what does Gauss's law tell us? Gauss's law tells us that the flux through the surface is equal to the enclosed charge over epsilon naught. So what's the enclosed charge? That's going to be positive Q minus Q, right? The sum of the two charges inside of here over epsilon naught, that's just going to be 0. So Gauss's law tells me that because I have no net charge inside of this spherical surface, that the flux through the surface should be equal to 0. But does that mean that the electric field is 0 everywhere on the surface? Well, we know what the electric field looks like coming from a dipole. We solved for that in the last chapter and drew the electric field lines. And remember, it looks something like this. Okay. Very close to the positive charge, the electric field lines move away, and then they return back to the negative charge. Look at what's happening at the surface here, right? On this side, remember the A vectors, right, are pointing radially outwards, and they're aligned with the electric field vectors on the top half of the sphere. Down here, again, the A vector points radially outwards, and now they're anti-aligned with those electric field lines. So up here, I'm going to have some, up here I'm going to have some flux on the, say, upper side that's going to be greater than 0. Down here, I'm going to have some negative flux, right, on this lower part that's going to be less than 0. And those two, right, have to cancel each other out to give me that 0 net flux. But you can see at any point along the sphere, the electric field doesn't have to be 0. So the electric field's not 0 everywhere on the Gaussian surface. It's just that the flux that that electric field contributes as I go around this surface, right, the positive contribution at the top is canceled out by a negative flux contribution from the returning field on the bottom, and I get no net electric, I get no net electric flux for this particular case. All right, what about this one? Oops, so there's a typo here. This should say Q2. So the electric flux is shown through two Gaussian surfaces, this gray one and this peach colored one. And I have measured, or I know what the electric flux looks like. And I'm relating that to some value of charge that I call Q. Can we calculate what Q1 and Q2 have to be in terms of that charge amount Q? Okay, let's see if you can calculate that. So I have those two Gaussian surfaces. I know the flux through each individual surface. Does that allow me to calculate what the charge on Q1 and Q2 are? Okay, let me go ahead and end the poll. Share the results. So a lot of you picked C. Let's see how we do that real quick. We know Gauss's law tells us that through any Gaussian surface, the flux is just equal to the enclosed charge divided by epsilon naught. So if I come up here through this peach surface, well, they already gave me the total flux. And I know that has to equal the enclosed charge. What's the enclosed charge in that peach Gaussian surface? Well, it's just Q1. I can see Q2 is not inside of that Gaussian surface, so this has to be Q1 over epsilon naught. So look, this already is telling me that Q1 has to equal twice Q. Okay, so I can go over here, so maybe it's this one, or maybe it's this one, or maybe it's this one. But I can eliminate A and B straight away. What about the lower expression here? Well, I know that the total charge enclosed in this gray Gaussian surface is Q1 plus Q2. Both of those charges are inside of this Gaussian surface. So I know that Q1, I just solved for it above, right? So I can see that Q1 plus Q2 had better be equal to Q, right? The numerators have to be equal here. But I know that Q1 is just equal to twice Q. I solved that before. So what does Q2 have to be for this equation to work? It better be equal to minus Q. So I can see here that the answer has to be C, that Q1 is twice Q and Q2 is minus Q. Any questions about that? Let me just pause and check if we have any questions on the chat. Okay, I'm not seeing any questions. How are we doing? Is everybody still there? Are people listening? You're answering the polls, so I guess I know you're there. Okay. So let's try to do now that we have this kind of idea of how flux is related to enclosed charges, let's try to do a more complete calculation and bring in this idea of symmetry that we talked about yesterday. So back in the chapter 23, we had asserted or stated that the electric field coming from a sphere of charge, if I'm outside of that sphere of charge, that it has the same electric field as coming from a point charge. So let's try to prove that using Gauss's law. Okay. So I'm going to open up a notepad here to do some of this work. So let's go ahead and make a diagram of this situation. So we're imagining that we have a sphere of charge. So here's a sphere and there's some total charge Q on it, and say it has some radius that we'll call R. And we want to know what the electric field is at, say, a point out here, point outside of the charge. We'll call it electric field ER, right? This is going to be radial distance R. And we know that we're looking at R is greater than big R, so we're outside of the sphere. Okay. Well, how are we going to calculate that electric field? We're going to do it using Gauss's law. Okay. Gauss's law says that the total flux is equal to the integral of the electric field dotted into dA over my Gaussian surface, and that has to be equal to the charge enclosed divided by epsilon naught. Okay. So in order to do this integral, we need to define a Gaussian surface, right? So these Gaussian surfaces are just mathematical objects or tools that we're free to choose. And here's the argument that I'm going to make. If I can pick a Gaussian surface that matches the symmetry of my underlying charges, that's always going to be the most convenient Gaussian surface to choose. And why is that? We argued yesterday that if we know that, say, my charges are distributed in a spherically symmetric way, that the electric field that's generated by those charges is also spherically symmetric. Okay? And that means then that I know that the electric field out here at this radius R has to point radially away everywhere to be spherically symmetric. And at this fixed radius little r, it has to have a constant magnitude over the entire Gaussian surface there. That's just a symmetry argument, right? That's just saying that I already know something about the shape of the underlying charges, that they're uniform, right, in angle, right? If I do any kind of rotation, I get back the same object, so the field has to follow suit. And why is that so nice? Because I picked a Gaussian surface that mirrors that symmetry. Now, everywhere on this surface, the electric field is going to be perpendicular to my surface, right? So if I define, say, the A vector that points radially outwards everywhere, now I can see that it's going to be aligned with the electric field. And that's great because that simplifies this integral, because now the dot product is just going to be EdA. I can get rid of the vectors, right? Remember, the dot product is just like EdA cosine of the angle between them. Well, now I know that cosine of the angle between them is just going to be equal to 0 because I'm using a symmetry argument to exploit that. And furthermore, I know that the electric field at that radius little r, because it's also following spherical symmetry, is going to be constant, and so I can pull that outside of the integral. I just have one electric field value, one magnitude over the entire over the entirety of my Gaussian surface. Okay. And so now this thing, the integral over all my little surface contributions, is just going to give me the total area of my Gaussian surface. So because I picked a Gaussian surface that followed the symmetry of the underlying charges, this integral reduces to just the strength of the electric field times the area of that Gaussian surface. And that has to equal the total charge enclosed, which in this case is just Q. We can see the entirety of the charge in that sphere is inside of my Gaussian surface, divided by epsilon naught. So by using symmetry, we end up with a really compact form for Gauss's law, and that integral, right, that surface integral is basically trivial, right? It ends up just being the electric field times the total area on that over that surface here. And we know what that area is now, right? That area is just the area of that sphere, that Gaussian sphere. It's just going to be 4 pi little r squared equals Q over epsilon naught. And now I can solve this expression for the electric field. It just says that the electric field is equal to Q over 4 pi epsilon naught r squared. Okay, look, it looks just like the functional form that we saw from a point charge, right? If the point charge was sitting right at the center of that thing with charge Q, it would have this functional form, right? It falls off like 1 over r squared. Here's my 1 over 4 pi epsilon naught, those physical constants that we've seen before. Okay. So Jacob is asking, what does the circle in the middle of the integral stand for again? Yeah, so that means that it's a special notation, meaning that it's a surface integral. Right, so I'm using one integral line, but really we're integrating over some two-dimensional shape. So it's basically a way of saying that I have to, right? It's a compact way of saying that this is some double, right? A double integral over some two-dimensional space. It's just saying use whatever dimensions you need in order to solve that surface integral. And look, I want to point out a few things. So using that symmetry, right, we basically had this really simple form for Gauss's law. And in one line, we got back this Coulomb electric field, right, this form that looks like what we got from a Coulomb, right, a Coulomb function, this kind of 1 over r squared behavior that we asserted in the previous chapter. And now we can prove that even as the charge gets extended, as long as it's radially symmetric, if I'm outside of that charge distribution, the electric field just looks like what I would get from a point charge, having all that charge concentrated at a single point. Okay. Make some sense? All right. So let's try a few more examples. Let's do 2 more. By the end of today, let's try to see if we can get through both of these. We want to also use Gauss's law to calculate the electric field inside of a sphere of uniform charge. And then the last one is going to be slightly more complicated. I want to show you what this looks like to extend to a more complicated integral, but something that's still workable, and point out a few things there. Okay, so let's work through these. Oh, before we go on to that next problem, I want to point out here that this 4 pi epsilon naught, 1 over 4 pi epsilon naught, remember that's this thing we were calling k. K is equal 1 over 4 pi epsilon naught for a while. And several people kept asking, why do you always want to write things down in terms of epsilon naught and not just call everything k? And the reason can be seen here is that this fundamental relationship between the electric field and the charges comes through Gauss's law, and that has just epsilon naught. And this 4 pi factor just came from the particular case of, say, a charge that has spherical symmetry, right? That came from some geometrical property of the charge distribution. And so that k term is not fundamental, but epsilon naught is a fundamental piece to this underlying physics. Okay, so you can see now that 4 pi term, right, just comes from as a special case for spherically symmetric charge distributions. Okay. So let's try to do this one. What is the electric field inside of a sphere with uniform charge? So let's draw a picture again. I basically have the same setup. I have a charge, it has radius r, and it has a total charge that we'll call q total. And now what I want to do is I want to look at some position inside of this sphere. Right? That's radius r. Now little r is going to be less than the radius of that larger sphere. And I want to calculate the electric field at that point. Now I can make the same symmetry arguments. This charge distribution is still radially symmetric, so I know the electric field better be radially symmetric, right? The electric field better point radially outwards everywhere along this object and also be uniform in magnitude around that surface. So I can make that same argument. So that means Gauss's law, I can still write it down as it's got to be the electric field at that position times the area of my Gaussian surface, right? That surface integral just comes out to be this simple form like we saw before, and that has to equal to the enclosed charge over epsilon naught. Okay. The left-hand side of this just says the electric field. What's the area of that Gaussian surface? Well, it's 4 pi little r squared, right? It's just the area, it's just the surface area of that Gaussian sphere that I drew. What about the what about the right-hand side here? What's the total enclosed charge here? Well, I can express it in terms of a charge density. Remember, we have this thing that's called the charge density, and that charge density is just like the total charge of that spherical object divided by the total volume of that sphere. So it's a uniformly distributed object. I know this is like q total. The volume of that sphere is going to be 4 thirds pi r cubed, right? The volume of a sphere. Okay. So I know the density, I know the charge density of these things. And while the total charge enclosed has got to be the charge density times the volume of my Gaussian surface now. Right? That volume is going to be smaller than that total volume on the other side. But I can also calculate that. That's going to be my density that I just wrote down underneath that sphere times 4 thirds pi little r cubed. And now let's solve this for the electric field. I can see that I have a factor of 4 pi on both sides that cancels out. I can see I have an r squared over here. I have an r to the third, so that leaves one factor of r here. And so I get that the electric field has to look like the charge density times r divided by 3 epsilon naught. So I used Gauss's law to find that the electric field is growing linearly as I get further away from the center of that sphere. And I've got some constant terms here, just that density, 3 and epsilon, and then it's falling off, as I get further away, the electric field is growing in strength like epsilon until I get to the surface, right? So it's growing, right? So what does it look like? I could plot what this looks like as a function, right? Let's say here is r. So this is a function of r, and this is the electric field. Well, we just saw that this thing is growing linearly while I'm inside of the sphere. And then we just saw before that when I get to the outside of the sphere, the thing starts falling off like 1 over r squared. And so we can see that the electric field has to look something like this. As I move away from the center of the sphere, the electric field is growing. Then once I leave the sphere, it starts falling off like 1 over r squared. And look, the nice thing here is, right, the way that we would have found this electric field back in the previous chapter was taking and dividing all this entire sphere up into tiny point charges or shells or something, and then doing some integral over all those different charges. And it would have been quite messy, but you can see essentially in one line, and exploiting this idea of symmetry, Gauss's law gives us the correct form for the electric field. Okay, now it's a little subtle because this is only working so smoothly because we're able to cleanly see what the symmetry is and pick the correct Gaussian surface. And if that's not the case, then it's very frequently true that trying to use Gauss's law is just as complicated as doing the superposition principle. But if you're in a case where there's a clean symmetry and you can pick a nice Gaussian surface to go along with that symmetry, very frequently Gauss's law will give you the value of the electric field almost straight away with very little calculation. Okay, we've got about 10 minutes left. Let's see if we can finish this second bullet. We want to know what's the electric field inside of a sphere with a charge density that is dependent on the radius, right? So again, I have a sphere that has some total charge Q total. It has some radius R here. And now I know that the density, the charge density, depends on how far away I am from the center. Okay, and it's equal to some constant that we're going to call C over R. Okay. Let's see if we can find what the electric field is at position R. Again, we can make the same argument we've been making before, that this thing is radially spherically symmetric, right? Even though the density is changing as a function of R, if I rotate it right around, that the charge distribution looks unchanged. So this electric field times the area of the Gaussian surface had still got to be equal to the enclosed charge over my epsilon naught. This says E, what's the area of my Gaussian surface? Again, it's 4 pi epsilon naught. No, sorry, not epsilon naught. 4 pi r squared. Now what's Q enclosed here? Well, they give us the charge density. So I know Q enclosed has got to be, say, the integral of this charge density times some little volume component. Over E naught. Right, I need to take some small volume component, and the density is not uniform here, but it's radially symmetric. So maybe you've seen in calculus, or maybe you can recall back to calculus, that if I have a radially symmetric integral, right, this has got to be a three-dimensional integral over that volume. But if it's radially symmetric, that reduces down into a one-dimensional integral that's like whatever the density is in R, 4 pi r squared dr. Okay, this little dv becomes this expression for a radially symmetric case. If you haven't seen that in your calculus class, it's okay. I'm not expecting you to be able to use that going forward, but if you recognize that, then that's good, right? It's essentially, you could go look this up in a table of integrals and see that for a spherical, right, for solving this three-dimensional integral in spherical coordinates, that this is what you would get here. And this is going to be over epsilon naught. And now all I have to do is plug in the functional form for that density. So that's going to look like the integral from 0 to say r of C over r 4 pi r squared dr over epsilon naught. I get that r canceling one of those. And what do I get? I get something that's going to look like 1/2, oops, times 4 pi, and then I'm going to get, and there's a C pulled out, r squared, has got to be equal to E times 4 pi r squared, something like this. Oh, look, a bunch of stuff cancels out now. I got a factor of 4 pi on both sides, and I have a factor of r squared on both sides. And I get this thing that says that E is just equal to C, whatever this constant is, divided by 2. Look, that's, sorry, yeah, over epsilon naught still. Thank you on the chat. There's still an epsilon naught in the denominator here. Thank you, Jacob. And that's a really interesting result because this says that the electric field is constant, right? It's independent of R. So if I were to make a plot of the electric field for this guy, it's just constant, right? This is the electric field as a function of R at C over twice epsilon naught until I get outside of the charge, and then we know it's got to fall off like 1 over R squared, because then I'd be outside of this charge. Now, what about C? We could also find C in terms of the total charge. Okay, that's just a physical constant. We can see the functional form. We could also find C, because I know that if I integrate that density over the entire extent of my sphere from 0 to big R, that this had better give me the total charge on the object. So I could solve that integral to find big C, right? This basically says from 0 to R, C over, what is it? C over R, 4 pi R squared dr has got to equal Q total. And then this thing, right, the R's cancel out. So this thing is going to be like C 4 pi over 2 R big R squared has got to equal Q total. Okay, and I could solve that for C, right? So I basically get, that's 2, that's something that says that C is equal to Q total over 2 pi R squared or something like this. Okay, so I could express C in terms of the total charge and the size of the sphere also, just by knowing the value of the total charge on here. But the really interesting thing is that getting this functional form out is almost trivial with Gauss's law, assuming that we remember our three-dimensional calculus and how to perform this little trick. Where if we did this from superposition principle, this would be a couple pages of algebra and calculus probably to figure this problem out. So exploiting symmetries is a really powerful idea, and it lets us quickly understand what the shapes of electric fields look like coming from some fundamental geometries or some shapes of different objects that we see in our system. Okay, we have about 3 minutes left. I think I'm going to pause here for today. Tomorrow we'll continue doing some Gauss's law problems. We'll look at using Gauss's law to rediscover the electric field from a sheet of charge and a line of charge, just to see that we can get those quickly from Gauss's law. And then we'll also talk about how to use Gauss's law when thinking about charges distributed on some conducting object.